Hello everyone. In this video, I will present my discrete event simulation model for a real service system that I observe, which is TZ, a beverage shop in Pondok Indah Hanau. Before I start, let me introduce myself. My name is Naban Arif. I'm from Industrial Engineering International Program. So the purpose of the simulation is to analyze the queuing problem that happens during peak hours and to evaluate performance of the current system using Simio. So first, I will explain the real system, the surface flow at TZ starts. So how this surface starts is first the customer enter the shop. After that, she or he will wait in line for the cashier, and then they will place and pay their order. After that, they will wait again while the drink is being prepared and finally leave the system after receiving the drink. So the process flow in my model is entrance, cashier, drink preparation, and exit. From the data that I observed, I found that the interval rate was within the interval of 15 minutes. I counted around 25 customers arriving. So from this, I calculated average arrival was 0.6 minutes per customer. As we can see from the data, I entered random interval time was random exponential zero point 0.6 minutes. After that, I also observed that the waiting time was 42 minutes in the queue, and the surface time in cashier was 1 minute. So that's why I put random exponential at processing time random exponential 1 minute. And lastly, when I wait for the drink, it took around 10 minutes. So that's why I put random exponential 10 in the processing time. Okay. Uh, I think that's all from the setup. Let let's run our model so we can see how does it actually work in simulation. When running a simulation, there's a lot of things that we can activate. For example, before I start the simulation, I already put the ending type to 1 hour because the observed time that we supposed to do was 1 hour. We can also see what actually happens in the model by seeing the model trace, and we can see when the customer enter the cashier, when customer exit the system, and so on. We can also fasten the process of the simulation by adjusting the speed, and we can also use real-time clock to to do the simulation. And if we don't have too much time, we can also forward it until the end of the data. Okay, the data is almost done. Okay, we can see that the data is finally done and the simulation is finally done, and we can see that there's a lot of congestion in the cashier and drink preparation area. We can see that the system is not working quite well, so that's why we will dive deep into our experiment so we can see what is actually happening in the TZQ system. Okay, so I also added several supporting measures, which are number in system, time in system, utilization of cashier, and utilization of drink preparation. So now I will explain the result. So from the time in system, I got that the it's 28 minutes for the average customer to wait in line, but and for a number in system, it's around 49 customers are in the system at the same time on average, and the utilization from cashier is 98%, and from the drink preparation is 97%. This results show that both service stations are operating at almost full capacity. This indicates that the system is highly congested and has a very limited space capacity during peak periods. So to interpret more, I will show you the small plot for the timing system. For the small plot and timing system, how to actually read it is so from what I can interpret, the small plot shows that the timing system is centered at around 28 minutes. Most applications fall within a similar range, although where there are some lower and higher values. This means the model consistently indicates long customer time in the system and support the conclusion that the current process is congested. And this is also the pivot grid. Yeah, I think that's all from me. And thank you for listening. Hopefully, this might be useful to you guys. And thank you.